Yeah, maybe we should start the second talk today. And we're happy to have Professor Robert Hardt from Rice University. He's telling us about homology and cohomology theory for metric space. Let's welcome.
Get that on. Everybody hear me okay? So it was like 1973 when I went to my first math conference. And I was kind of nervous and stuff. And I remember a couple things about that conference. One was the outstanding lectures that Blaine gave on minimal varieties. And you know, the enthusiasm and the deep mathematics. And I also remember, you know, how nice he was. And all these things are still true today. So I'm very honored to be able to attend this conference, let alone speak it. Okay, so today I'm going to talk about some work I've done with mostly with Thierry for a while. I'll give sort of indicate how we got into this a little bit later. And the two papers, one has appeared on chains, and the other one is on dealing with cochains. It's with Thierry and Washek Pfeffer. So, okay, so this is a very big kind of problem that we've all thought about. For given a homology class in a space or a cohomology class, try to find some kind of special representative cycle or cocycle. And you can first try to get a sort of a simple theory by using adapted to the spaces, the kind of spaces you're looking at. And as we all learn, you know, if you triangulate spaces or something, you could use simplicial theory, or for smooth manifolds and real coefficients, you can use differential forms or Drum theory. And say semi-algebraic sets, you can work with semi-algebraic chains. But you can also look for special representatives from a variational problem. For example, in Hardt's theory, Riemannian manifold, you look at harmonic forms, and they minimize an L2 norm in a Drum class. Or also classically, geodesics provide length minimizing cycles if you've got a Riemannian manifold again in a one-dimensional integral homology class. So historically, this example and the obstruction, I guess, started by Pauw back in the 50s, something, that there may not be smooth manifold to represent higher dimensional homology classes. These led to the question of existence of perhaps mass minimizing representing cycles. And this was one of the motivating problems for the work of Federer and Fleming in 1960. So in this paper, where they kind of invented sort of the modern currents and rectifiable currents and so forth, they weren't just looking to solve a higher dimensional absolute plateau problem of finding a least mass object with given boundary, but they also were looking at the problem of minimizing mass in a given homology class. And if you don't have like a smooth representative, you know, what would happen with a minimizing sequence of smooth representatives or something like that, or you know, what kind of singularities might develop. And so this required the chains in their homology theory to have a suitable notion for mass, and importantly, a suitable topology, so you can maybe take limits of mass minimizing sequences. Okay, the chain should also include, in particular, finite volume submanifolds and have some kind of geometric structure. So in '59, famous paper in Yale, they proved that integer multiplicity rectifiable chains give the ordinary integral homology, at least in the category of pairs of Euclidean Lipschitz neighborhood retracts. And homology classes of such pairs contain the mass minimizing rectifiable chains. And so there's a kind of a standard picture we think of a minimizing homology class that of this. Let's see, how do you do this? This guy here. Oops. Hit the wrong button. Sorry. Okay. I don't know where my pointer is here. So maybe we can switch. Oh, there it is. Okay. So this is the I'm sorry. Okay. There's one point. Let me just click. Okay. So this is a standard picture we think of. You have a curve representing non-trivial one-dimensional class in the torus, and the minimizing one is over there at b tilde. Okay, so Euclidean Lipschitz neighborhood retracts include compact smooth manifold. They include polyhedra, but they don't include pieces of algebraic varieties. So if you just have a simple cusp, think of your cusp in the plane, that's not a Lipschitz neighborhood retract of its, not a retract under a Lipschitz map of its boundary. So this is one of our motivations, is to have some homology theories to do this. So what are rectifiable chains? Okay, so first let me talk about rectifiable sets. So a subset of a metric space is rectifiable if roughly it's the image under a there we go, pushing buttons again. It's the image under a Lipschitz map of just a m-dimensional measurable subset of Rm. So it's just an image under a Lipschitz map plus maybe a little set of measures 0 and with the m-dimensional Hausdorff measure. Okay, so but you can sort of do a little better by a theorem of Federer. Essentially, I think that you can parameterize parameterization theorems. There's you can take this set and you can get the same set X or the same rectifiable set by finding disjoint compact sets in Rm and an injective map from a finite countable union of these sets to M, which aren't just Lipschitz, but which are bi-Lipschitz, with the Lipschitz constant of the inverse universally bounded just depending on M. So you can, so the picture there maybe is sort of, you have these, in the domain you just have these regions in Rm, and in the range you have this sort of stack of images which are disjoint, but it's not a locally finite family in the image. So of course the rectifiable sets turn out to have all kinds of tangential properties that they enjoy. So let me describe rectifiable chains. Now I'm going to be talking about general chains with coefficients in a general complete normed abelian group. So if you don't know, a norm on a group is just what you would guess it to be. A norm of A plus B is abelian groups, I'll do it with addition. The norm of A plus B less than the norm A plus norm B, and norm of the norm equals 0 if and only if the element is the identity. So, and we're going to use the norm because we want to talk about some kind of a mass for these chains with G coefficients. And so we get a rectifiable G chain just simply, we just add to our parameterization, we just add a density function, which is G valued and integrable. And then you have to do some kind of identification with this definition. It's not just a formal sum, but you've got some identifications related to the sort of standard picture you have in when you define manifolds and so forth. So we're really looking for the object here with some kind of a multiplicity, and if it's parameterized one way or another way, then the multiplicity should really be the same at corresponding points, except for maybe a plus or minus sign, depending on orientation. And so that's the way if you think about it for a second, how you would define a rectifiable chain. In the case where G is like the reals or subgroup of the reals, like the integers or something, then you can actually get a current then you can use the chain to integrate differential forms. And that was the case in which Federer and Fleming considered. But I want to talk about the general G chains in this talk. Okay. So anyway, these form an abelian group. I'll just use that notation Rm for the rectifiable chains. Okay. So before I go to metric space, I'm going to make one remark that we all should know. This is almost the second thing you should know about metric space. It's due to Kuratowski, and I think some people will say, maybe when metric spaces were defined earlier, that maybe for that it was even known then. But metric space admits a distance-preserving map into a Banach space. And the proof of this is worth knowing that there's a very easy formula for this. If you have a dense subset of the metric space in a fixed point, then you can just consider the map from the metric space into bounded functions on the subset. Just take the distance to the point x minus the distance to the fixed point. And of course, you see you can also view this as going into continuous functions or into Lipschitz functions. But the idea is you're using the soup norm on the space you're embedding into. And so identifying x with the image under this embedding, you can think of x itself just being a subset of L infinity. In particular, if it's a separable metric space, then it's essentially just a subset of little L infinity, usual little L infinity. So that's all metric spaces. Separable metric spaces are just subsets of little L infinity. Okay, so we'll view that. So let me take care of some of the standard definitions here. Actually, with chains, the idea in talking about these things with chains is a little bit different from what you usually do with currents. With currents, you define some huge space of distributions, and then you start putting conditions on the distributions to describe what it means to be down to this geometric object as rectifiable current. When you deal with chains with coefficients, you really have to get them by starting from the inside by elementary objects and putting a right topology and doing completions. So let me talk about these sort of elementary objects like you see in algebraic topology. So for its obvious definition, kind of for mass of our parametrized rectifiable chain, you just integrate the multiplicity, the norm of the multiplicity over the set, and that gives you a notion of mass, one notion of mass, and so we're going to be viewing these things as being in the Banach space Y for now. So I can in the Banach space I can talk about drawing straight lines and stuff. So a polyhedral chain is just simply a finite sum of these parameterized guides where you just have a affine map and you have a closed simplex and you have a constant on each simplex. That's all a polyhedral chain is. Then the Lipschitz chain is the same kind of thing, except you allow yourself to have Lipschitz maps into Y, so they can be curved a little bit, but they're still locally, they're just finite sums of pieces with constant coefficients. Okay, so let's use that notation for the P and the L for the groups of polyhedral and Lipschitz chains. And then you have a not hard to prove theorem that the rectifiable chains that I've described are the mass completion of the Lipschitz chains. The mass completion of the polyhedral chains, by the way, are kind of interesting things for sort of very special variational problems. But you know, if you have something curved, to approach it in mass, you can't approach it in mass by a polyhedra, but you can approach it in mass by a Lipschitz. So polyhedral and Lipschitz chains, why am I talking about them? Because they have an easily defined boundary operation. The usual way you know the boundary of a polyhedral chain, and you have the boundary of a Lipschitz chain just by putting the appropriate plus or minus sign on the boundary simplices and considering the restrictions. And, but these boundary operations are not mass continuous on the polyhedral chains. And in fact, as like the Koch snowflake, that is the, the standard fractal snowflake in the plane shows you the boundary of a rectifiable chain. So this is certainly a rectifiable subset of the plane, the inside here. But this boundary guy is, in no sense, finite mass. So this is not, the boundary of that rectifiable guy is not rectifiable. So in order to talk about the boundary of that thing, again, we're not just working with currents, we're not in some dual space. To talk about the boundary, it requires completion of these spaces where you do have a boundary. But you have to complete it with respect to a sort of a weaker norm than mass. And this is, Whitney invented flat chains way back in the 40s, 50s. And the flat norm, so the first motivation for the flat norm is, I've heard about this a little bit before, that if you just have a sequence of points 1 over I approaching the origin, then at the point they certainly converge. But if you look at the corresponding zero-dimensional chains, sort of point masses, they don't approach the origin in the mass norm because the mass of the difference is 2. It's 2 points. But they do. Whitney defined a flat norm where you do get convergence. So for a Lipschitz chain T, you can define the flat norm of T as this infimum of mass of S plus mass of T minus boundary S, such that S is one higher dimensional chain. So the picture here for the case of the converging points is that you see that this point is, as zero chains is converging because it bounds an interval of length whose length is going to 0. So, and the general situation is the same kind of thing. You make the connections to, you try to make a connection or a homology between different chains to measure their flat distance. And okay, so it's a beautiful, really beautiful geometric notion. And, so I say since the flat norm is a norm on the Lipschitz chain, that requires a few pages to prove. By the way, that's not the hard part of that is showing that just the if the Lipschitz chain has flat norm 0, then it's actually 0. But anyway, we can define a group of it is a norm, and you can define the group of flat chains. Now it's simply the flat completion of the Lipschitz chains. Or if you're in the Banach space, just you can also do the flat completion of the polyhedral chains. Either one gives you the same thing. And so then the boundary operator is the flat continuity of the boundary operator on Lipschitz chains gives a well-defined boundary operator on the flat chains. And so now our original problem was looking at a rectifiable chain. Since the flat norm is less than the mass, then the rectifiable chain now has is actually flat, and so it has a well-defined boundary. So now we understand the boundary of that Koch curve as a sort of a flat chain. Okay, so this allows us to make a bunch of sort of easy definitions, but these will be, and I'll give some examples, but these will be sort of relevant. But you have a lot of possibilities here. And in the Federer Fleming paper, they sort of discussed homology using flat, using flat rectifiable normal chains. So you can just do as I expect. You can define the flat cycles as, I'll just talk about the absolute one. I won't do the relative versions of these things. So you have a flat chain T, and you have the supportive T is in X, and supportive boundary T is 0. That's a cycle. And of course, for dimension 0, what you mean by cycle is by sort of augmentation. Then a zero-dimensional flat chain. There's this So zero-dimensional kind of rectifiable chain is just a countable sum of point masses, and this extends, and then this chi, this augmentation is just this total multiplicity of the thing, and this extends to the flat chain. So that's sort of what you mean by cycled when you have 0 dimensions. It's a necessary condition for the thing to be a boundary. Anyway, so in all the dimensions you have the flat chain homology groups, cycles divided by boundaries, and so that's fine. But you can also start put restrictions and on these chains that you work with. And one of the ideas that I didn't maybe indicate enough at the beginning is in considering other homology theory that sometimes you're not just interested in the algebraic topology of the space, you're not just interested in some standard topology, you're interested in maybe topologies to reflect properties, like in our case, the metric. So you can look at so-called normal chains. These are a terrible word that Federer used. He always used to complain to me about the words normal and regular being used too much in math, but he did it too. And so normal chains just means that finite mass and finite boundary mass. Finite mass, finite boundary mass. And, sorry. Okay. So you can work with either the normal chains, or you could work with the rectifiable chains, which happen to have rectifiable boundaries. Those are called, integral currents. Either one of those, and then you can define corresponding homology theory the same way. Okay, and I'll just give one trivial example here to indicate some difference here. If you have this picture here and we consider the boundary here, remember the boundary is a nice well-defined flat chain, and now we're going to pretend we're living in the space X, which consists of this boundary. So we're like a circle. The space is like a circle topologically. Then there's the normal one-dimensional normal homology of the thing is 0, and the one-dimensional rectifiable homology of the thing is 0, simply because there is no one-dimensional guy of finite mass here, or of finite mass, which is supported in there, has a non-trivial that has boundary 0, no non-zero one, and then of course, but the flat chain there is, and so that's kind of giving you back the second one is giving you back the sort of the ordinary homology of the thing, but maybe these other ones are giving you some homology reflecting the metric. So it's really easy example, but just to give you a feeling for this thing. Okay, so now I want to pause a little bit and talk a little bit sort of words from the sponsor in some sense. What was the motivating thing behind this was these plateau problems. So I'm going to say a few words about mass minimizing G chains. Very few words about this, but I want to include some of the results relevant to that. So I'm going to give a very, very short history. So I apologize to all the references I'm going to be leaving out. But this is of the sort of the higher dimensional plateau problem past dimension 2. In 1960, Federer and Fleming used chains with R as coefficients in Rn, and the chains were currents. They called them rectifiable and normal currents. And they're studied as understanding them as linear functionals on differential forms as currents. And then in 1966, Fleming, and of course one of the points of this was they solved a general higher dimensional plateau problem in Euclidean spaces by doing that. Well, Fleming observed there's some problems where you can actually work with chains with coefficients in a finite abelian group. That was way back in '66. And so this is one picture, one sort of easily motivating picture. For a minimal Mobius band, in other words, you have a Mobius band which is like a minimal surface 2 and sort of looks like that. that can be viewed as a chain with coefficients in Z2 that, with just two elements. And as a chain, boundary of A precisely means that it's that circle, unoriented circle. So this makes sense. And you can, he showed that you can do the compactness and the minimizing mass, and then later the regularity and so forth. So this makes sense. Incidentally, I should point out something I talked about. Bill Eller, this is in Bill Eller's thesis, dealt with some boundary regularity questions, and that was just a few years after this. So I guess the thesis was about 69 or so, and he dealt with like unoriented minimal surfaces. So following his thesis, at that stage, one knew that any, for example, any finite collection of smooth closed curves in Euclidean space would bound a embedded minimal surface with boundary, regular thing like this. And so, 10 years later, Leon and I sort of got some credit for doing this in the oriented plateau problem, and there was harder technicality. But actually, Bill's thesis showed this for unoriented things. So unoriented, it's quite general fact. And he already had both the interior regularity of Fleming and his regularity up to the boundary for this thing. Anyways, his thesis I don't think was published either. I mean, which is strange. It's very well written. But he got off into varifolds and became famous for varifolds and stuff like that. But I just want to point that out. Anyways, if in that's sort of a mod 3 example that makes sense here. If B is 3 similarly oriented semicircles, like in the picture, the dark thing, then they bound, and the angle there is 120 degrees. They bound 3 the half disk. Then as mod 3 chains, these semicircles are a cycle that has this, because 3, boundary 3 equals 0. So and these 3 half disks, in a precise sense, have that as the boundary. And so this was dealt with in Gene Taylor's thesis a little bit, the sort of using these mod 3 chains in 2 dimensions in 3 space to sort of picture a lot of minimal surfaces you see, which have this kind of a 120 degree angle thing there. So anyways, there's other applications of these things with these finite coefficients. I know Brian White wrote a nice paper on fluids of different groups of immiscible fluids and stuff. But speaking of Brian White, and the 2 papers that really got us going in this subject were from around 2000. There were 2 beautiful papers. One was by Brian, who he sort of generalized Fleming's work. He had much more general norm dealing groups, and he obtained new regularity proofs, which are some of the simplest now for the regularity theory. And about the same time, Luigi Ambrosio and Ben Kersheim talked about currents in a metric space using a definition, I think, from DeGiorgi. And so they did some generalization for currents, and that was kind of generalizing Federer Fleming. And so our goal was to kind of do some context to do both of these together. And there were some other works, which I won't go through all these in the intermediate times and so forth, but many people talking about geometry, and particular geometry in metric spaces and sort of geometric variance theory currently formed. I'll mention a couple of these as I come to them. So let me state a theorem. An important property relevant to the existence of mass minimizing chains is a compactness theorem. And let me state this. So suppose X is a compact metric space, G is a complete norm abelian group, with closed balls being compact. So I've got to have some compactness on everything, the space and the norm and the metric. So so for any positive R, if you look at those flat chains with mass and the mass of the boundary bounded by R, then this space is sequentially compact. And okay, so that's sort of providing a basis for doing a plateau problem, where you sort of minimize mass, and you have some compactness, and but to get more geometry in the thing, so it's not just like an abstract current or something like this, that you have some rectifiability of the thing. That's also rectifiable, and this is in case the group, the precise condition discovered by Brian was that the group now contains no non-constant Lipschitz curve. So if you think about that for a second, that doesn't apply to the reals. So it's not true for the reals with the ordinary absolute value. I mean, there's your Lipschitz curve, the real, it's the interval joining them. So, but all the finite groups, it's certainly true, discrete groups, and then there's some other ones, p-adics and so forth, that are a little more exciting. But under that condition, somehow, then you do have this compactness for these rectifiable currents. You have this sort of thing. So the point is the rectifiability in B gives the sort of a geometric character to your plateau solution. They kind of look like manifolds or something, multiplicities and singularities. So while this rectifiability is not true for G equals R with the usual norm, it is true if you put a different norm on R. So I just want to show you just sort of kind of an application or something of this. I'm using an example here, and I'll just show a picture here of transport paths in various applications. Think of the mail, for instance. So often it's efficient to put things along the same path, more efficient than to have them go separate paths. So we may consider formally two probability measures, mu and nu on Rn, and view these probability measures as zero-dimensional real flat chains. And then you can, so that should be a real there instead of just the G in that group. And we can choose a T to try to connect them. So we're trying to connect probability measures. So we can do this trick of taking an alpha less than 1 and defining this norm R to the alpha by just the absolute value of R to the alpha power. Then this group here, the reals with this norm, this group norm, it's not a vector space norm. Okay, it's a group norm. You just talked about the addition. You're not saying the norm of T times V is equal to absolute T norm of V. You don't, no. It's a group norm. Norm of A plus B is less than norm A plus norm B. That works if you have R to the alpha. Then it does satisfy that condition. And merging paths in T may reduce the corresponding mass. Let me call it M alpha of T to remind us that we're using that other norm. So just one picture tells you the whole story here. Let's consider joining these 2 point masses here, mu, to these point masses here, and I'll put pluses here and minus there, and then try to connect them. So if I dealt with the usual one-dimensional current joining them, then there's no question that the least mass one would be the dark one there, the dark blue or dark black connection, and that's mass 2. And but there's another way to connect them with currents. You can sort of bring them together and then have multiplicity 2 and then separate out afterwards. And that's kind of like what the mail does, right? You know, the mailman picks up the mail at different locations, puts them on the truck, carries them someplace, and maybe merges some more, and then they separate at the end. So anyways, you can do your calculations here that if you do this, take to the 1/2 power of these things, then this is just multiplicity 1. So it's just 6, there's a distance 6 each way. On the other hand, and these are just multiplicity 1 here, so you just have 4 times the square root of 2 for each of those little segments. But going across here, which has length, ordinary length 2, you have square root of 2 because it's a multiplicity 2. Okay, so it's so you have square root of 2 times, it's length, 4 steps there. So anyway, these numbers add up to a smaller number. So it gives you with this alpha norm a smaller number. You know, the no Lipschitz path thing, you know, you have the real with this alpha norm, then you know you have the distance between these 2 points. The metric distance is just the distance to the alpha power, which is a nice finite number. But if you ask for the path distance, you know, you try to make a path between these things. What's the path distance? Well, that means you've got to divide it up into little bits and then add up. Divide up, and as you do that, you're going to go to infinity. So this is not Lipschitz path connected with that norm. But anyway, this is the handy use for that norm to just do that variational problem. And Shaw, several years ago, showed the existence of these things, and he showed actually a nice rectifiability theorem that even though you have real coefficients here, if you stay away from the boundary, then it's actually just a finite structure here, just a bunch of intervals coming together with appropriate angles. So that's a picture of connecting the point math to the one-dimensional measure on an interval. So it's sort of this. And then higher dimensions, and we haven't finished writing this up, that we do sort of a problem related to the soap film. And so this says that if you do this M alpha minimization in arbitrary dimensions, then you actually get with the singular set of dimension m minus 1, you kind of get this whole geometric measure theory, regularity theory, like Almgren's theorem, but it's much easier. It turns out to be much easier with the alpha less than 1 because it wants to bring things together. And so the multiplicity, it allows us to handle the multiplicity problem by sort of squeezing things together and have to do that. So, we also think this is true for R too, but I don't want to claim that because I don't know. We haven't looked at that in detail yet, but I think it's also true for the reals, the higher dimensions. Okay, so let me get back to that normal compactness theorem, and maybe I can say take 5 minutes to go through this proves. This will be the most technical thing. I'll just zoom through this, so just that maybe you can get a few words out of this. But so what were you trying to prove? Let me see where we're back to. We're trying to prove this number 1 here, that this set of flat currents with mass and the mass of the boundary, and we're in a compact metric space. There's some better theorems where you don't, other theorems where you don't put the compactness on the space stuff. But let's just, for simplicity, we're in a fixed metric, compact metric space, and we've got these bounds on the mass and the mass of the boundary. And okay, yeah, I'm sorry. I didn't explain M hat. This from another side. But anyway, it's not hard to show that this is complete. And then we just need to show it's totally bounded. And so the usual proof of the sort of total boundedness in this is involved what's called the deformation theorem, where you kind of take your currents and you push them onto, you do an approximation by a specific sum of chains which live in the faces of a fixed skeleton. And that allows you to sort of get your total boundedness. Now, in our general setting, we can't do that initially, but we want to sort of, that's what I mean, totally bounded. We want to find this fixed compact set so that it's in the tubular neighborhood of those. We land up using a little functional analysis here. There's something called metric approximation property for L infinity that allows you to get actually a Lipschitz one linear projection down into a finite dimensional space so that you don't move things very much on your fixed compact set when you do that. That's the different approximation properties were somehow senses in which Banach's norms could be approximated by finite dimensional ones. And anyway, that's enjoyed by L infinity or other convenient spaces like C01 and stuff. So anyways, once we get down to the finite dimensional space, then we use the deformation theorem. The particular form of Bryan-White is originally due to Federer and Fleming. And you deform onto a complex. So I'm going to zoom this a little bit. So you sort of do a homotopy with respect to your projection, and then once you get down in Euclidean space, then you deform onto the complex, and that gives you your thing. But, so it just some functional analysis goes on there. Okay, and the second result involves a couple beautiful proofs. We steal one from Brian and one from Ambrosio Kirchheim. The one for the dimension 0 is a very, very nice argument. Brian, maybe I say that this is to show the rectifiability. Now we're in dimension 0. Rectifiability just means it's just the countable sum of point masses. And so we use this lemma here, which is kind of interesting. It says if you have just a measure theory lemma, if you have a positive Borel measure without atoms, then there's the measurable function, all of whose levels have measure 0. It's not hard to get this. So then we apply the lemma, following Brian's idea, to the total variation measure for the non-atomic part of T, if T had a non-atomic part. And then, let's just say for non-zero mu, we would get by this property, by this lemma here, this guy, you look at the inverse image of 0T, because the inverse image of the point T is measure 0, this is continuous then. This becomes a continuous path in the group. Okay, we take this is all a finite mass, zero-dimensional chain. It's like a G-valued measure. So we get this curve in the group, and that'll have mass less than T, and then you can of course reparameterize the curve to have to be Lipschitz, and you get a contradiction. So maybe I won't say much. The higher dimensional thing, roughly speaking, this is kind of related to Pauw's talk a little bit. You're looking at the slicing the current by projecting onto Rm, and you're viewing the current as kind of like a graph, not of a multi-valued function, but of a function whose values are these finite sums of point masses. Anyway, that turns out to be a BV function. And then some Ambrosio Kirchheim said BV functions can be approximated by a Lipschitz function, and that sort of gets you into the rectifiability. But so let me go on a little bit. Or are there any questions about this? So I just wanted to indicate a little bit of the sort of the plateau problem behind this thing, and this is sort of the goal in this paper and the Ambrosio Kirchheim, some of these other works, was to sort of get all the basic hard rectifiability theorems in GMT, use very general context. So, okay, now I'm going to say a few words about duality and cochains. That'll be my last topic here. This is related to our. So for simplicity, for the rest of the lecture, and yeah, we're only going to be talking about the duality in the easy case of the reals. Okay, so for the rest of the lecture, we're switching gears. Don't have the general G. We just have the reals, and we have. So now the normal chains are a vector space, finite mass and finite boundary mass. And if you want now at this stage, if you sort of understand about integrating some kind of forms of Ambrosio Kirchheim, they're not, these forms that are used to define the metric space currents are not quite so as good as the usual differential forms. You don't have this sort of the same topology coming from the form. You don't have d squared is 0 and stuff like that. So But the main objects are the dual objects, the currents in the metric space. But anyways, so we have cycles, those things with boundary zeros. We have the zero-dimensional cycles, those are now, you can view those as just ones where you evaluate on the function 1, you get 0. Okay, and now the zero-dimensional ones are just signed Borel measures. Okay, finite total mass. Okay, and that's the homology cycle modulo boundaries with the normal one. So we're just doing the normal chain, normal homology. Okay, so Whitney also studied the dual space of flat cochains with the real coefficients, the ordinary dual space, and under the and then in this case the norm is a vector space norm. And his student Wolf in '57 proved that a flat cochain can be represented by a differential form. That is, that you take the cochain applied to the current should be the current applied to the differential form. But the form is only assumed to be bounded Borel form, or generally bounded measurable, but bounded. Actually, you can get bounded Borel form, and where d omega is also in a distribution set is Borel. Then Dennis Hardt and Steve Keith in a couple papers, they studied these kind of so-called flat forms or something to study the question of Lipschitz equivalence of the Euclidean space. And Marie Snipes, student of another student of also considered some generalization to Banach spaces, the notion of partial form. But we won't get into that. Now we look at a different linear space, a different dual space. So that was the dual space of flat chains. We're going to look at sort of a natural dual space of normal chains. Called the charges. And these were first defined by Pauw in sort of the zero-dimensional case, or to study solutions, classical solutions of the equation divergence v equals f. And they're asking questions in particular, when you can, for what f's can you find a continuous v to solve this equation? And they've used these things sort of, the terms in the divergence theorem as functionals of the region omega, sets of finite perimeters. So I won't say any more than that about the specific result there, but one of the things they did show that when they went to the corresponding thing in Hardt, they called it forms of cochains in middle dimension, meaning not just the top dimension or the bottom dimension, but all dimensions. And they showed that quite generally charges in Rn correspond to a continuous form plus d of a continuous form. So any charge in Rn can be related to, it can be given, it can be put in that form. And, we haven't been able to get this corresponding thing in metric spaces, but so let me give you the formal definition of charges, and as sort of motivation for it, if you work with BV functions, then you typically, you have the so-called BV compactness theorem or something like this, but you don't work with the BV norm directly. What you do is you consider weakly convergent sequences where the BV norms are bounded. So norm-bounded convergent sequences. This is sort of typical situation in calculus variations where you do this kind of look at these kind of convergences, and this is actually the general procedure of localizing the topology to get this. In our case here, we'll just define this localized topology T sub n on Nm. It'll be essentially defined by sequentially in that a sequence TJO converge T in here if and only if it's flat convergent and the sup of the masses and the boundary masses are finite. Of course, we're working in a fixed compact set. If you didn't have a compact set, you should also fix the supports to stay in a fixed compact set in your localized topology. Then a charge is just a continuous linear functional on this linear topological space, NMN with tau t. And these are so-called charges. Okay, so it's some kind of dual object to normal currents. Then you have the co-boundary defined, sort of dual to the boundary, and the pullback of charges dual to the push forward of the chains or currents in this case. So here's the theorem. It's not a real deep theorem, but it gives some indication about this homology and these. So the normal, it says consider the following three conditions. The normal chain homology of the space is 0. The zero-dimensional normal chains homology is 0. And the fact that X is the Lipschitz path connected, any 2 points can be connected by a Lipschitz path, or that the charges cohomology in dimension 0 is 0. Then actually A implies B and B implies C. And so here's an example that you don't get the full circuit. So this example is probably worth looking at for a minute or two, because it's a very easy example. It's a very, very naive example. Okay, the difference here. So X is just a finite, countable union of curves with some multiplicities. So they're all, let's see, what about these things? They're all curves. They join some point AJ to 0. Okay, so you've got a lot of these curves. They're disjoint. And let's see, what about the curves? Okay, the length of the curves are the length of the jth curve is, or I guess. I's curve is, can't read my own writing up there. I's curve is 2 to the I is the length. And, okay, right. Okay, so let's consider the boundaries, start taking boundaries of these things. And first, if you consider this zero-dimensional chain given by taking this with the origin with a +1 here, multiplicity, and the ith one here with a multiplicity 2 to the minus I. Of course, all these minus multiplicities, sum of 2 to the minus I adds up to 1. So this t here is has the chi of t equal to 0. The total multiplicity is 0 of that. And this space is Lipschitz path connected. Each of these paths are a finite length. So you take any 2 points, you can join these things. And but T bounds no one chain of finite mass, because if you had a one chain of finite mass, sort of by roughly a constancy theorem, then you'd have to have a multiplicity of 2 to the minus I multiplicity on each of these things, and then you've got the length of 2 to the I. So then when you multiply those together and add them up, you get infinity. So anyways, there is a condition, nevertheless, it does allow you to get this. C does imply C will imply A if your space satisfies the linear isoparametric condition. So that just says that given a boundary, then there's some constant depending on the space X, so that given any boundary, then it can be filled in by a chain whose mass is less than a constant times the mass of the boundary. That's a linear isoperimetric condition, and then we'll just say X is M bounded if you've got this condition in all the dimensions, in dimension M. And this linear isoperimetric condition has been studied by many people. I think of Gromov with the hyperbolic space, hyperbolic groups, so forth, and up till Stefan Wenger used this linear isoperimetric condition in his papers in recent times. And as soon as I said this to Dennis the other day, he sort of pointed out that Whitney that's really what's the heart of using kind of Whitney's idea of the sort of what you carry over from like polyhedra, that you have this kind of you need these kind of estimates. Anyway, they suppose X is M bounded. That is, have this linear isoperimetric condition in all the dimensions. Then the boundary of S is closed in that topology. The boundary operator it's closed, and the d bar guy is closed. So you sort of want this closed business when you take ratios. When you look at form homology or cohomology groups, these are now typically infinite dimensional spaces. So you want to mod out by closed subspaces. And so using the corresponding charge cohomology groups, the kernel of, as defined before, except special case here. So we define the charge cohomology just like we do dual to the charge homology using charges. We have this duality theory that on the category of pairs of compact metric spaces satisfying all the M-boundedness conditions in relative versions, then these guys both satisfy the Eilenberg-Steenrod axioms, and these two functors HM and H lower M dual are naturally equivalent. So I should point out that these, the norms are preserved under this duality. The norms are preserved. So just to relate this, in '74, Federer proved a duality theory using real flat chains and flat cochains for the category of Lipschitz, Euclidean Lipschitz neighborhood retracts. And so our goal in working with normal chain homology and charge cohomology is to understand these spaces, metric properties of spaces, typically where, like, varieties or fractals or Gromov-Hausdorff limits, or various other things. All these things I said are limited because we've got some kind of word rectifiability coming in someplace. So they don't apply to things like spaces that don't have rectifiable, non-trivial rectifiable sets, such as the Heisenberg group or something. But whenever the rectifiability is present, we want to sort of get some stuff out of it. So some natural questions here are to determine which spaces are M-bounded. We've been working on a project. It's not quite complete, but hopeful that it's showing that the varieties are actually M-bounded. So that would be a kind of a really important application of these things. And also I've said something about H0, but not about the higher M's. And you want to think of the space X being, like possibly having a lot of infinite stuff going on into it too. So these are typically like Banach spaces, so with normed spaces, so the norms are relevant. And of course, the problem you always state whenever you have variational problems at some stage, it's not known their regularity whenever you have some kind of mass minimizing guys here. So I guess that's it. So thank you very much.
Any questions?
Yeah. Well,
you had this regularity theorem.
Yeah.
You put the norm on the alpha.
Oh yeah, sure.
It said that the minimizers were polyhedral.
That was in one dimension.
Oh.
Okay. Yeah. So, but it is a non-trivial thing because what you start with is all you have initially, that was Shaw's theorem, that all you have initially is a sort of a vector value measure. You know, I mean, that's sort of finite mass, flat, so-called zero-dimensional, or one-dimensional finite mass flat chain is like just a vector value measure. And so you have to prove that actually, you know, you have all this stuff, tangent cones and so forth, and that you actually have this sort of nice discrete structure, and then it ends up being just away from the boundary polyhedral. Of course, as you get to the boundary, you get more and more of that bifurcation and so forth. And then we were kind of claiming a similar thing for higher dimensions with much less. I mean, we just had the singular set of dimension n-1, but yes, and we were just doing the integer coefficients in higher dimensions, but I think it's probably true for the reals also. That you get. So yeah, so to just say a word technically about what goes on in that sort of general plateau problem, the key lemma that says that, you know, once you've got several multiple things, that if you have a minimizer and once you're sort of close to a disk with high multiplicity, then it has to actually be sealed together along the large set, most of the set. It's actually a single sheet with high multiplicity. So it's already got the multiplicity. So that means in the so-called Lipschitz graph approximation, you actually just have a single valued function. Unlike the nightmare case of Almgren's theorem, you know, where you have this like a square root of z or something like this, square root of z to the z cubed or something, where you have, you know, you can very close to a disk, multiplicity 2, and you know, they don't come together. You know, they stay apart, and then you have to deal with branching and branching and branching of higher branching. So that's why it's, you know, I'm a big regularity paper, and that's why the Lawson and Spadaro are spending so much time trying to shorten the proof. Yeah. Yeah. Pauw? Oh,
Do you have any clarification? The homotopy groups, subspaces.
Yeah, that's a very good question. And before I started talking to you a few months ago, I wouldn't have thought about that. No, but I don't know anything about the homotopy groups of these. Yeah, but it's probably worth you and I talking about this a little bit. You know, get back to Texas, because that's especially interesting. It's probably interesting in low-dimensional things and stuff like that. You know, and right. Yeah. I mean, the motivation behind a lot of this is just sort of doing the GMT in singular spaces, but the singular spaces is, you know, like I say, either varieties, sort of concrete, or more worse things, you know, like the Bromo-Hausdorff limits of smooth things, or, you know, various things. And so we just have sort of various soft theorems where you can have a context to work these things. Yeah. Yeah.
So the p-adics were satisfied.
Yeah, that's funny, isn't it?
So have you looked into that?
No.
Results?
Yeah, no, there must be some interesting applications that. Yeah, right. That's right. Yeah. Because. Yeah.
You had this nice example of
Yeah.
male problem. But is there any way of sort of directly posing the male problem and coming up with that norm for someone? Or is it
no, the half was just because it was less than 1. Just for my computational simplicity there, of course. It's true for any alpha, of course, you still have the same quantitative thing. You just have different angles and stuff.
The question is there any way of start with the male problem and come up with that norm?
No, it just, you know, when Shaw was doing a thesis, that seemed to be just something that would work. And,
male probably has a large fixed cost, even if you're carrying no letters. It's a small marginal cost.
Yeah. No, certainly the male. Yeah. That's right.
Plus.
Yeah. No, after Shaw's thesis, that's sort of a big kind of group in Europe has been working on various kinds of things. So, and in fact, as John says, in real practical problem, there are probably some sort of bounds on various things, you know, and combinations of things. But it is sort of something, you know, this combined transport, shared transport, you sort of, you know, the veins in your body, you see it everywhere, you know. You sort of see the things. Right. Any more questions? It's already 10 after, so I don't think we'll take one. Thanks.
Thanks.